Okay, I think now we should be on, we should be streaming. Hello, hello. Is everyone on here? We already apologize for being 2 minutes late. Okay. Jonas, how are you doing today?
I'm good. How about you?
I'm okay.
Good.
Perfect. People are getting online. So, do you mind if we start around 5 minutes past 8 here? I mean, if we start in 2 minutes?
No problem. No problem. It's also
Perfect. So, can you guys online hear us well? Bonsoir. Il y a Aurélien Bonobono qui vient de dire bonsoir. Can you see the chat, Jonas?
yeah, I can see.
Perfect.
Yeah.
Can you guys online hear us? Yes, okay. Thank you, Futse. Hello, Michael, Nana. Hello, Jero. So we are starting in 1 minute. Hello, Safi. Hey, Dr. Paulin. Jonas, you have a huge fan base.
It's not. I'm happy to see so many people.
I mean, we are starting this series of KmerAI talks, and then we will see week by week who had the highest fan base. We will see.
Okay.
Okay, in 1 minute, we are letting Jonas do the magic. Hey, Jonas, you're getting greetings from Mikael Nana Kameni.
Hey, hi, Michael.
You see, you have big fans.
Hey, hi, Bertrand.
Okay, it's 5 minutes past 8, GMT plus 2 time. I think we are gonna start. So, welcome everyone to this KmerAI series talks. We are inaugurating these talks with Jonas NGNAWE. Jonas is a PhD student in computer science at the University of Laval and Mila-Quebec AI Institute, working on local robustness of deep neural networks. Jonas here holds a Master's of Engineering in Computer Science from École Polytechnique Yaoundé, a Master's in Mathematical Science from the African Institute for Mathematical Sciences, and a Master's in Machine Learning at AMI, the African Masters in Machine Intelligence. Before starting his PhD, he was also a Google AI resident at Google AI Lab in Accra, Ghana. Welcome, Jonas.
Thank you, Liz.
Jonas today is gonna take us through his latest work entitled Detecting Brittle Decisions for Free, Leveraging Margin Consistency in Deep Robust Classifiers. So, Jonas, I will give you the floor and then switch off my camera so that all the attention is on you.
All right.
Okay,
I think
perfect.
my camera will stay on, I guess.
Yes, please.
Okay. So, thank you, Liz, and thank you everyone for coming. So I'll present this recent work that I did with my team, Sabi, Yann, Frédéric, and Christian at Université Laval and in Université Côte d'Azur in France. So so the outline of the presentation will be the following. First, I will introduce, make an introduction, then I will present the problem and our contributions. And then present the concept of margin consistency and the evaluation and the results, and then before giving some perspectives and concluding. So deep neural classifiers are machine learning models for classification that are based on deep neural networks. So you can see them as a black box with two components. First, you have this feature extractor with a linear head. So what typically happens is that you have in the task of image classification, for instance, which is what we'll focus on in this talk, you have an input image, X, which is you can see as a vector in Rn. In practice, it's a matrix, but you can see it's a long vector of pixels, which goes through the feature extractor, and then you get a certain representation called the feature representation in another space. It's also called the embedding. And then you apply a linear classifier on this representation at the end, and to get another vector in another space, RC, where C is the number of classes, and it's called the logits. And the prediction is made, whether it's a cat or anything else, by taking the maximum value of the logits. And then you can get a probability distribution from the logits by applying the softmax function. So in computer vision, there is a challenge. There has been a challenge for visual recognition on a data set called ImageNet that some may know. So the objective, so if you have models, they can predict for a given image what are the top 5 predictions, like top 5 labels that you could give to that image. So it appears that deep neural networks are very powerful models for this task. And at such a point that in 2012, the first deep neural network to win that challenge, AlexNet, reduced the margin, the top 5 error from 25 to 16. And since then, the performance kept decreasing until it got better than an average human performance. So you can also, they are really they really do great on this task, and deep neural networks are also powerful in other domains of machine learning, such as machine translation, for instance, where they also kind of transform the field. So unfortunately, like a bit like 1 year after AlexNet, like 2013, we also discovered, like researchers discovered, that they are also vulnerable to adversarial examples. So what is exactly an adversarial examples? Let's take, for example, this cat image here that the model predicted with 99% confidence. And we add some small and carefully crafted noise to it. You get the following results, which is still looks like a cat, no difference. But your model will predict this as 99% guacamole, which is avocados, basically. So it has nothing to do with the original image, which is like the cat. So this is called an adversarial attack on the image. And this existed before in machine learning with other models such as SVMs. But the particularity with deep neural networks is the contrast that you have with the high performance. This kind of mistakes an average human being would not do that kind of mistakes. So that's the particularity with this vulnerability in deep neural classifiers. So it's a whole field on itself. I could make another presentation on adversarial attacks or adversarial machine learning if people are interested. But yeah, so you could tell me why is it important? So it's important because the same kind of adversarial examples can happen in real life. So you can have, for instance, a stop sign with a certain luminosity or with a certain graffiti on it can be mistaken or misinterpreted for a speed limit, which could be dangerous. And it also happens with other modalities such as voice or videos on all other modalities. And for instance, how are you with small noise could become a voice command for open door. And even in the era of large language models, the adversarial attacks do still exist since their discovery, like since 2013. So it is an important issue because these models are sometimes deployed in sensitive and safety critical systems, and in these systems, a failure could mean like could cost lives. So it is important to have models robust to this kind of sensitive to this kind of perturbations or failure, and even more if we could detect them. So now let's talk about the problem and that we are dealing with and our contributions here. So the notion of robustness that we are dealing here with is called local robustness. So robustness to this kind of perturbations. So there are many definitions in the literature. The one that we consider here specifically is robustness in the LP sense, which is we could also call epsilon robustness. It is basically invariance of the decision within a certain area around the sample. So let's see what it is visually. So if you have 3 samples here in your input space, and you have a model that you train the model with this decision boundary, you can see that these samples are at different distances to the decision boundary. And if you were to evaluate their robustness with respect to a certain threshold epsilon, if you draw these epsilon balls around the samples, what you notice is that for these 2 samples, x1 and x2, you can cross the decision boundary and stay inside the epsilon ball. That is like you can add some noise with this magnitude and you cross the decision boundary. So x1 and x2 will be called non-robust. And you will notice that x3, no matter what you do, you will not go out of the dotted line, the dotted circle. So this sample is robust. You cannot cross the decision boundary inside here. So that's what we mean by robust or non-robust. So in general, if you want to evaluate your robustness in terms of local robustness or adversarial robustness, what people do is to compute the robust accuracy of the model, which is the probability that a sample is correct and robust. So what is done in general is that you perform something called adversarial attacks on the test on a given test set. The standard one used in benchmark these days is called auto attack, and the objective is to determine for each sample if it is vulnerable to attacks or not. So if you could perturb it with noise and you get a different label, with a small noise and you get a different label. So you determine that for each sample, and then you give a ratio of how many were correct and robust. So the question is, what if you want to know in a real-time deployment context that information? If you have a sample, can you know in real time if you want your sample is vulnerable to attacks or not? So it could be to reduce risk, or you want to monitor samples, or you could be taking a decision about prioritizing resource. So the 2 options you have mainly are either you attack again the samples, or you use a formal robustness verification, which is like a certification method to tell you if, with certitude, if the sample is robust or not. So the problem with these two is that both are still computationally expensive in that context. That means if you want to attack a sample, it will take you a certain time, even 1 minute or 5 minutes, depends on the model, to know if the sample is vulnerable or not. So it's kind of, you cannot do that in real time. What we know in one hand is that if you know the input distance for certain, if you know the input distance here, the input space margin, which is the distance to decision boundary in the input space, you could decide with exactly if the sample is non-robust or not. So this is the input distance. The input space margin is the perfect score for the detection of non-robust samples. The problem is that for general deep networks, this is not, this DNX, you cannot compute it exactly. You cannot, it's intractable. You cannot even compute it because it's an NP hard problem. And so on the other hand, what you have is the margin. You also have a margin in the feature space. So in our setup, as we see before, our neural network is composed of a feature extractor, then of a linear classifier. So what happens is that you have a sample X here in the input. It is projected with the feature classification, with the feature extractor, you get a certain representation Z. And then you apply your linear classifier, and then you take the decision about the class. And in the input space and in the feature space, you also have this output distance here, or not output, but the distance in the feature space, distance decision boundary in the feature space, which is tractable because you know it's a linear decision boundary, so we know exactly how to compute it. So the formula here is, so in this formula here, Q is the dual norm of P being the norm here in the input space. And so what we did is, so the interesting thing is that with the distance in the feature space, if your classifiers are equidistant, that means if this difference, the norm of this difference here is constant, you can express this exactly as something proportional to the logit margin. So the logit margin is the difference between the biggest logit, which is assuming the sample is classified as class I, that is the biggest logit, and the second biggest logits. So that's the definition of the logit margin that we will denote in the following as in the sequel as D out. So in this work, what we introduced is a concept called margin consistency, which is a property of robust deep classifiers, as a rank correlation between the input margin and the logit margin. So we'll dive into that shortly. But what we showed first is that we show that it is a necessary and sufficient condition to use the logit margin for non-robust detection. And secondly, we experimentally showed on CIFAR10 and CIFAR100, which are image datasets, that most robust deep classifiers are strongly margin consistent. And then we experimentally showed that the logit margin of strongly margin consistent models can be used to detect vulnerable samples to attacks, and then we can estimate the robust accuracy on arbitrarily large data sets using a small subset of the data. And then finally, we showed that in cases where the margin consistency is weak, we can learn pseudo margin from the feature representation that correlates better with the input margin. So let's see what the margin consistency is before looking at the results. So let's come back to our examples where we consider these three samples in the input space. You have these three samples. And what happens is with the feature extractor is that you apply the feature extractor and you get on X1, you get Z1. You apply on X2, you get Z2. And you apply on X3, you get Z3. And then you apply your linear classifier with the linear decision boundaries. And you get the distances to the decision boundary in the feature space. So the margin consistency property says that if X1 is closer to the decision boundary than X2, and which is also closer than X3 in the input space, in the feature space, Z1 will also be closer to the linear decision boundary than Z2, which will also be closer than Z3. That means the order of the positions is preserved. And so we can define it formally by saying that there's a monotonic relationship between the input space margin and the logit margin. And since it's correlate, so it's a monotonic relationship, so we can use the Kendall rank correlation tau to measure the margin consistency. So here, an absolute value of 0 would mean that we have no margin consistency. And if we have an absolute value of 1, that would mean we have perfect margin consistency. So the first thing that we show is that this theorem is that margin consistency is a necessary and sufficient condition for the logit margin to perfectly separate non-robust samples from robust samples. So to give you an idea, so this theorem says two things, like that first, let's assume you have the input margin on the x-axis, and then you have your logit margin on the y-axis. So it's simply, the first thing you can say about it is that if you have this monotonic relationship, which is like the margin consistency increasing here, a sample that is non-robust on the left side of a red sample here on the left side of this threshold here in the input space will also be less than a certain threshold lambda 0 in the logit for the logit score here. So if you have margin consistency, you can have also a threshold that perfectly separates the red side from the green side here. The second thing is that if you don't have the margin consistency, so if you have, you obviously don't have the monotonic relationship, you will always make a mistake using the logit margin. That means, for instance, if you have these two samples here, which are which is X2 here is non-robust because it's on the left side, and X1 is robust because on the right side. But if you try to separate them, for example, if you take this line here, you will correctly classify X2 because it's below, but X2 is below, but it is not. You will say it is non-robust while it is not. So no matter where you draw the line, you will always incur a mistake. So why this theorem is important to establish? Because we can now say that the level of margin consistency can tell us the discriminative power of the logit margin. So that's why it's important. So let's see the contributions which are more practical on the evaluation and the results. So in terms so the experimental setup is the following. So we consider two data sets, CIFAR10 and CIFAR100, which are image data sets. Usually they are used for robustness evaluation. And then in terms of robustness, we consider the L infinity norm, which is the maximum pixel, basically. And then the threshold that you use for robustness is 8 over 255, which is approximately 0.031. So for the models considered, we loaded pre-trained model from this benchmark called Robust Bench, which is a benchmark for this kind of robust models. And we also trained some ResNet 18 models on CIFAR10 with some popular adversarial training techniques. And then we estimated the input margin by computing the norm, the distance between a sample, a clean sample, and its adversarial counterpart. And this adversarial counterpart is computed using an adversarial attack called fast adaptive boundary attack, which can give you the smallest, the closest adversarial example if you give it sufficient budget. So you estimate this over the 10,000 test samples. And then with these estimations, you can create a pool of vulnerable samples at your threshold here by just separating them. And so the first thing we check is the margin consistency. So what you see here is a plot of the input margins in the x-axis and the logit margins in the y-axis. And then you can see this monotonic relationship I was talking about earlier. So the Kendall tools are expressed here. For most of them, it's above 0.7, which is very high for the Kendall tau correlation. And so what it means is that if, for instance, on this CIFAR10 here, you can see that if the input margin is small, you will also have a small logit margin. If the input margin is large, then you also have a large logit margin. Then we use this property to detect vulnerable samples. So we measure the detection here with the standard detection scores. So mainly the area under the ROC curve, the area under the precision recall curve, and then the false positive rate at 95%. So what you can notice that for models with high margin consistency, so with Kendall tau absolute value greater than 0, from close to 0.7 or beyond, you can see that the OROC and the AUPR are like very high, and the false positive rate at 95% is also smaller than compared to like the two models with the small margin consistency. So this is the performance at epsilon equal to 255. So we also try to vary it to see how it would look like if we varied the epsilon. So if you vary the epsilon, you can see the variation of the ROC curves and the precision recall curves. So if you're not familiar with these curves, just know that a random classifier, if you were just to randomly say if a sample is robust or not, then your performance would be here, like this first bisector here. And then if you have a perfect classifier, like an oracle, then your performance would be like the green one here. Same on the other side. So you can see that the performance stays quite high no matter with the variation of the epsilon, which is like consistent with the property of margin consistency. So the second thing we did with that property is to efficiently estimate the robust accuracy using few samples. So what's the problem here is that if you have a test data set of n samples, in this case, you have 10,000 points in your test data set, and you want to evaluate the robustness for a certain threshold. And the problem is, can you estimate that robust accuracy only using few samples, let's say 100 or 500 samples. So what we do is to randomly select a subset of size n from the big data set. So we select, for instance, 500 from 10,000, and then you compute the estimations of the margins on this smaller subset, and then you create ground truth labels for the vulnerability threshold, and then you determine what is the threshold of the logit margin that gives you the best robustness, robust accuracy approximation on that small subset. And then you use that threshold on the bigger data set to determine the ratio of correct samples that are beyond that threshold. So in practice, how does it look like? So here we have our evaluation on CIFAR10 and CIFAR100. So on the x-axis, you have your models and the robust accuracy evaluated. So what you have in blue is what you can see is the evaluation on the 10,000 test data sets. So what you can find it on the robust bench website or what is evaluated. And then in orange, you have what we estimated using only 500 samples. So you can see that for most of the models on CIFAR10 and for almost all models on CIFAR100, the absolute difference between what we approximated with 500 and what was computed with 10,000 is quite small. So you can have an idea of how robust your model is without attacking all samples, basically. So then if you have noticed in the results, there are these two models that have a weak margin consistency. So you can see that their curves are not, like for instance, it's almost flat for this model, non-increasing. And the approximations also were quite big. So the question is, if you don't have the margin consistency, what can you do about that? So the answer we provided is that you can learn a pseudo margin to simulate that margin consistency. So we used an architecture from a paper, a Université 2019 paper called used for confidence prediction to say if a sample will be misclassified or not. So we use the same architecture where you add a multi-layer perceptron to your architecture, basically, and then you train. In this case, we train the model, this multi-layer perceptron, to predict the distance, the margin. So we just do this by minimizing the mean squared error between the estimated distance and the output of the MLP. So this appeared to like simulate the margin consistency. So basically what we obtain is that for these two models, before you train, so if you use the logit margin of the model, you have a very low Ken delta with bad performance. But if you train the pseudo the ad hoc model to get the pseudo margin, you can have a higher margin consistency, and you can have a better performance on the detection. So visually, it means that the curve of the relationship between the input and the logit margin or the pseudo margin now will kind of become now more increasing. So two things about, so I want to say something about like what this property is versus what robustness and Lipschitz smoothness is. So the property of Lipschitz smoothness for a model means that the output will not change we change by a factor of at most we change at most by a factor of L of the input. So it is important for classifiers because if you have a small L, then you have also a high robustness. That means your output cannot change by a certain cannot change arbitrarily, even if you perturb the input. So the thing to note here is that margin consistency is different from the robustness itself. So robustness or elliptic smoothness does not imply margin consistency. You can be robust, but you may not be margin consistent. And you can see this by the cloud points here, where you have the robustness versus the strength of the correlation. And you can see that models with different robust accuracy can have similar Kendall tau, basically. Yeah, so let me go to the perspectives and conclusion. So there's two things, two perspectives here. The first is about the vulnerability scope. So if you've noticed, so the robustness that we measure from the LP robustness definition is the distance to the decision boundary, which is like the worst case view of local robustness. So there is another way to measure this, which is like measuring the area around the sample, that is in the other side of the decision boundary. So you can note that you can have two samples with the same distance to the decision boundary, but the red area here is different. So it's bigger here and smaller here, depending on the curvature of the decision boundary. So you have so when we say we detect vulnerable samples here, we specifically detect them in the sense of using this worst case view here. So it's unclear if if the margin consistency can help also predict the average estimation, which is something that we haven't looked at, which could be a ground for future work. And the second thing is the influence of neural collapse. I will say something quickly about it. So what is neural collapse? So neural collapse is a phenomenon that was discovered about deep neural classifiers. So it says that when you train a deep neural network beyond zero cross entropy loss and beyond zero training error, the feature representations, which are the dots you see here are the feature representations, will collapse to only few states. So if you have you have three classes. Beyond that regime, you will every sample that you will have will only be in these three states. So you can no longer have a logit margin. It's like for any sample, you only have three logit margins. So in this case, if we attain the neural collapse state, we can no longer recover the information about the input space. But in practice, of course, we do not attain this state. And an interesting question is to see how does the margin consistency vary with when we approach a neural collapse state. So this is also something that could be looked at. So so I don't know how much time I did, but I will conclude. So to conclude, in this work, we introduced a concept of margin consistency, which is an order preservation property of input margins in the feature representation space. So first, we showed that it is a necessary and sufficient condition to use logit margin for non-robust detection. And For the and we also showed that for the majority of robust diff classifiers, they are strongly margin consistent, and we can use the logit margin for these classifiers with strong margin consistency to detect vulnerable samples to adversarial attacks, and we can also predict like the robust accuracy or measure the robust accuracy at scale using just few samples. And also, the last thing we did is to learn to show that we can learn a beta correlated pseudo margin even when we don't have high margin consistency. So that's all for this presentation. Thank you. I'll leave it there.
Thank you for your presentation. Actually, I didn't ask you in the beginning. Can you hear me, Jonas?
Yeah.
Okay. I didn't ask you in the beginning if you would prefer like an interactive session, so with the questions coming in while you're presenting, or if you want them at the end. So I just reserved them for the end. I hope you don't mind, and get and the guest in the comment section also do not mind.
No problem. I think it's better you take the question to go it order, and then you tell me which questions I should answer.
Okay, so first we have a question from Safi. She's asking, please, how does auto attack works? So I think it's somewhere around the 9th slide or so.
Yeah, it's way at the beginning.
Yeah.
So
And
uh-huh.
please, for everyone who is in the comment section who is listening to the live, please go ahead with your questions. Just post them, as we have a lot of time now for them.
Yeah. Okay, so I mentioned auto attack later, I think, when I was introducing how we evaluate. But as I said, I could do a whole other thing about how attacks work. But auto attack is a set of 4 different attacks. So it's not just one attack. So it's a set of 4 attacks. And 2 of these attacks, so you have most of them are iterative attacks. So you have, so it's a, they have diverse. So the general thing you have to know is that it's a diverse set of attacks. Some are gradient based, and some are black box. And then the general way that an adversarial attack works is that, so if I go to this thing here, is that you just start with the sample at the beginning. So for one attack, for a given attack, what you do is that you keep pushing the sample in a certain direction until you cross the decision boundary. So you push it in the direction where you maximize the loss instead of minimizing the cross entropy loss, if you want. So when you are training the model, you minimize the cross entropy loss so that
Yeah.
so that in this case, you are maximizing the loss. And then you maximize, but you keep the noise that you add in a certain range. And then, so that's basically how every attack works in general. So based on on how you approximate the grad, so you take direct gradients, of course, to go to the decision boundary, but depending on how you take the gradients, if you can compute the gradients directly in a white box case, we call it a white box attack. And if you can just approximate the attack, or you don't have access to the attack, to the gradients or to the architecture, we call that a black box attack. So auto attack, in short, is a set of 4 different attacks. Yeah.
So if I understand correctly, in this kind of setup, you are not minimizing the loss, but you are maximizing it.
Yeah, to create this sample here, like you see this.
Okay, so the objective is different from
Yeah,
correct classification. Okay.
yeah. So how do you create that noise? That's what we call adversarial attack, basically. How do you create this noise here?
Okay.
Yeah.
And so you, at the end, you reach the ideal adversarial noise when you have shown that by adding this amount of noise, you switch,
Exactly.
you can
Exactly.
switch the classification. Okay.
Exactly. So after pushing, adding noise, after some point, you can, if there is a budget, of course, you cannot do this indefinitely. So you have a certain budget of iterations, for instance, and then after some time, you check if you have crossed the decision boundary, if you have changed decision. In this case, you add some noise after a certain time. The image still looks the same because you are adding small noise,
Yeah.
but the label has already changed for the
Yeah.
model. Yeah. Cool.
Um, I hope, Safi, your question was answered. So we have another question from Bertrand,
Mhm.
who is asking, should I understand that based on your results, the adversarial noise on the cat will not be recognized as a guacamole?
Yeah. So there is yeah, it's an interesting question. So the type of detection that we do here is to detect if this cat, if you add this noise to the cat, it can become a guacamole. There are two types of detections that are different. So there is a task called adversarial detection, which the objective of adversarial detection is that if I give you a sample that was on which a noise was added, can you tell me if the model will be misled or not? Like if the model will tell guacamole instead of cat. That is adversarial detection. The detection we are dealing with here is that for this sample here, can we say if by adding some noise with a certain threshold, it will become, it will be misled for guacamole. So let's see what robust, and that's exactly the definition we said at the beginning. So we are detecting if these samples here can be perturbed to change their decision. So detecting this sample here is different from detecting if this sample can be perturbed. So X1 and X2 here can be perturbed because can be attacked because you can cross the decision boundary inside this ball. And for X3, you cannot because no matter what noise, so this is certified. So X3, you could use a certification method, the robustness verification that I talked about at some point, to show that no matter what you add to X3, whatever noise you add with this threshold within the dash room, you will not cross the decision boundary. So the X3 will be robust and the others will be non-robust. So so we are detecting if samples is robust, can be attacked or not. So vulnerable to adversarial attacks or not, which is slightly different from saying if a sample has been attacked. So that's
Okay.
this only distinction. I hope it
Okay.
answers this question.
I kind of had the same.
Mhm,
I had kind of had the same question as Bertrand because I was wondering,
mhm.
yeah, what's important? Is it knowing whether a sample is robust? So by sample you mean an instance, right? Is
Yeah,
it
an instance, yeah, a sample, yeah.
knowing that an
Vulnerable.
instance is robust, or making sure that it is, or making sure that we can still do the correct classification even though it's perturbed? Because then I am wondering, does it mean that your approach is a kind of, it, can it go under pre-processing, then kind of identifying which instances out of my data set will then be robust, and then I can train my model only on those?
Uh, yeah, I understand the question. So the question of, so you are talking about how you are like suggesting a way to robustify the model to make the model robust, right? So these, when you want to make the model robust, it's called adversarial defense. So if you want to defend your model against adversarial attacks, there are many strategies for that. The adversarial training that I talked about, one of some of the adversarial training strategies is just to show, is just to attack samples and to show it to the model. It's data augmentation. You just do data augmentation
Yeah,
with the attack samples
yeah,
and you train it with it and then you make the model robust.
yeah,
So that's the most common defense strategy.
yeah,
But then the interesting thing is that if you know how to detect, so the detection, to detect, you have to have the detection needs the model, because the detection is more like, if I have a sample and a model, you cannot do it before having the model. If you
Yeah,
have,
but then the question is, when I know that after training, when I know that my samples are robust, what do I do with the information?
okay, so that's why I came to this slide. So
Okay.
there are two things. The first thing, if you were doing adversarial detection, if you were to detect if a sample was attacked or not, that is more like a defense.
Mm-hmm.
In this case, I just talked about three scenarios here about that you could use, but more in real time. But it's more about knowing uh, how your model can resist to noise. So when you are doing it off, like when you are evaluating your model, how robust it is, what you do is to give that information that is a sample vulnerable or not to attacks. Now, if I understand your question, it's like, why is it important to know if it's robust or not? Is it the case? So you may, so you, it's about how you take a decision. Assuming you are using it is deployed on a self-driving car, right? And you know that this, you know that a particular
Signboard.
sign or can be
Signboard.
attacked, yeah, yeah, like yeah, a sign or some object can be attacked, right? If you know that information, you can take some action based on that the decision. So I the decision you make about that information can be depends on the application, of course, but it is important to know if your decision is vulnerable or not. And it
Okay.
will also be to monitor, because if you have a lot of samples, and you kind of want to know which samples will be perturbed. So it will be important to, if you can know this information in real time, then you can can pick. But in general, the decision at the end, it's another kind of decision. Like, what do you do when you know that this sample is vulnerable to attacks? It's more based on the application. If you are in a medical domain, uh, uh, where I think they are less studied there, but if you're in medical domain and you're taking a decision about cancer, you're detecting cancer, if your sample, if your data set was corrupted and you are making a prediction about someone's life on that, and you don't know if this sample can be attacked or not, then it can be it create a lot of risk. So the decision depends on the domain, but at least you have the information that your decision can be vulnerable at this point. So
Okay,
yeah.
I think I kind of understand. It's something about it happens at inference, and it's maybe something around a prediction interval or like a confidence interval for the prediction. But I will come back to it. But let's
Okay.
go around the table and take others' questions first. So we have another question of Safi. She's asking what percentage of noise changes the label?
Changes the level. So it
Yeah.
depends. So that depends on the model, right? Like so on it depends on the model and the data set. For so that's why we evaluate the robustness of the model. If the more robust the model is, so if the model is very robust, let's assume the model is 100% robust, which does not basically will not exist. Let's say close to robust, which like 100% accuracy, right? If it's close to robust, then no matter what noise you add, there will be no change. Like even if you add the biggest noise, the noise with the biggest norm, which is for L infinity norm is between 0 and 1, there will be no change. And that's the case. Let me show you the example with X3
Yeah,
here.
extreme.
X3 cannot change, even if you add the biggest noise possible with this model. X1 and X2 can change with this noise level. So the noise level depends on the sample and the robustness of the model. And as I showed on CIFAR10 and CIFAR100, in general, the robustness level that is considered small is 8 over 255. And that's what we consider robust, and that's what is used for evaluation.
Okay, we take the next question by Aurélien Bono. What are some potential limitations or drawbacks of using margin consistency for detecting Brittle decisions in CNNs? Kind of, can your method be applied to other type of architectures?
Yeah, there are CNNs. So in my okay, sorry.
It's okay.
So I have a diverse set of architectures, and it's mainly on ResNet models. So yeah, you have the list here of the architectures here. So most of the models studied for robustness are generally ResNets, wide ResNets, or the pre-act ResNets. And so these are made of convolutional layers. But you also have transformers. You also have transformer model. In general, it is, I would say, it is agnostic to the architecture. Like the property here just tells you how the input and the output are correlated. You can take any model, zip classifier uh, that you consider as composed of a feature extractor and a linear head, and you can measure with this Kendall tau how good your margin consistency is. So if you know that information, you can measure this for any model, whether it's CNN or a transformer or whatever. If you know that information, then you know that you can use just the output by doing a forward pass. You can use the forward pass and know if a sample can be attacked or not. So the drawback is not linked to the architecture itself. It's more like on the model or on the model that you train, because it doesn't matter if it's it has convolutional layers or it has the transformers. So it's transformers. So you just need a feature extractor and a linear head, basically. Yeah.
Okay. But can I can I come back to this question, because you keep on saying it's related to the model, but I thought the robustness was on the instance itself, in the sense that whatever architecture or model I am training, is this particular instance vulnerable to attacks? So meaning, yeah, whatever model I am using, I could eventually be able to change the decision boundary for this instance.
Yeah. So yeah, the property. So the it is what is linked to the is related to the sample and the model is the robustness. So given a sample,
Yeah.
it can be robust for this model and not for this other model. So it depends on the sample and the model at the same time.
Okay.
So
Okay.
what I was saying is more about the property of margin consistency. Uh, I thought that this question was about that. It is a property of the model because it just tells you how your input varies, like how the if your logit margin, which is like an approximation of your distance in the output space,
Yeah.
is correlated to the input. That is for the model itself. Now, if you know this, right? For the model, you know that any sample, you can measure you can know the input distance without attacking, just by taking the output, because the model allows you to do that. If the model doesn't allow you to do that, because it is not margin consistent, then you cannot use the property. But the robustness doesn't change for the model. The sample will be robust or non-robust, but you will not know that. You cannot detect that based on the margin consistency using the logit margin. But the robustness will not change, basically. I don't know if it makes it clearer or
Yeah, it's better. We have a question from Paulin, who is asking, I'm wondering if all the deep learning classifiers follow this generic architecture. For example, when the dense part of a CNet is a multi-layer perceptron.
okay. So Yeah, that's an interesting question because like in so it isn't it is not that you cannot have a linear head that is a multi-layer perceptron. It is that what I consider here as the feature extractor. So it's a nice question because at the beginning, if I show the, let me go back and then I can answer it
Yeah.
more accurately at the beginning on how I consider this.
Yeah.
Yeah. So I call this uh, feature representation and embedding. Yeah, actually, as he rightfully mentioned, sometimes you have a feature representation, and then there is some fully connected an NLP that is applied here. Just that if you can still model that thing in this framework. So it's like I force the I how do you call it? I divide it in that sense. So in this case, what you will do is that you only consider the linear head of
Classifier.
the classifier, the multi-layer perceptron that you added, and then what comes right before you will
Yeah.
add it to your feature extractor. So what we call feature representation or embedding here might not be the strict meaning of what we call embedding, depending on because sometimes when we train base models or what becomes now famously called foundation models, you can have something with features that you will use depending on your context. So we don't call feature representation specifically what comes out of this model base model, but everything that comes right before we apply the last linear layer. So
The
that's what we
classifier.
call feature extractor here. So it's a bit it's kind of a language precision that needs to be clear. And yes, if you have a deep classifier, basically you do some extraction, and then last thing is to apply some linear head to it, whether the head is multi-layer perceptron. I hope it clarifies this.
So basically, if you stack multiple layers in between your original input layer and your final classification layer, if I have, let's say, a transformer architecture just
Mhm.
before my output layer, I just need to go and look at the margins on this last before classification layer, so on my transformer layer.
So yeah, you could do that. I think that case I haven't considered, but what you could do, so what we do exactly, like for in the case of transformer models here, you is to go until you reach the last model you apply before the linear head, or the linear classifier. So here, what we call the linear head we have here is just the what produces the logits.
Yeah.
So that is what we call linear head. So what if you want to measure so what we measure as so the linear decision boundary that you have, it will respect to this. So let me show you how the projections I was making when I was doing the thing. So you see, when you project in this feature space that I call feature space, right?
Hmm.
You apply a linear decision boundary. So it means because it is a linear decision boundary that we are talking about this margin consistency that we can compute. So you have to go to the feature representation that allows you to linearly classify. It's as if your data set, so generally it's like your data set is it's like it's not well separated in the input space. So what
Yeah.
the neural network is does is like to
Make it
spread
more separable. Yeah.
until it linearly separates the things,
Hmm.
the samples, and then you apply your linear classifier to it. So it kind of brings it to a state where you can apply directly a linear classifier.
Okay.
So what we call feature extraction is everything before you apply just one linear,
Your
just
output
apply the
layer.
linear. Yeah, yeah. But it's not strictly the feature representation that you might understand from a model that we will use to fine tune or on another problem or something like that. Yeah.
We have a question from Lionel. What
Mhm.
is the benefit of using L1 norm in the feature space, meaning L0 norm in the input space? Did you try something else?
Okay. For norms, in terms of norm for robustness, so the different norms give you different type of robustness. So in vision, so the norm in vision class in image classification task, the usual norms are L2 and L infinity. That's what you will find in the robust bench. But L0 and L1 are also studies, but not as much.
Admirating, he meant L infinity. The L00, it's actually L
Okay.
infinity.
Ellie, what is he said? What is the so the question was
What is
what?
the benefit of using L1 norm in the feature space, meaning L infinity norm in the input space?
Oh, in the input space, what we use in the input space is L infinity. So normally the feature space, the input space for the property itself, in the input space you have L infinity or whatever you define for the robustness, and in the feature space, what you just consider there is the dual norm of the input space. So basically you just have to define the input space norm, and then the output the distance in the feature space is just given by it's just computed using the dual norm of p. So so p and q are related by a relationship that is called the Hölder equation. It's like 1 over p plus 1 over q equal to 1. So for L infinity norm, the dual norm is 1, and for 1, the dual norm is L infinity. So that's the relationship between it. But in terms of choosing which norm you use for the robustness, that depends on your problem. L infinity norm for an image is just the maximum pixel. So if you were, it's just what is the norm of this model? You just look at all the pixels and just take the maximum value of the pixel. That becomes your L infinity norm. So it is the most studied because basically, probably because it means that just having modifying just one pixel, for instance, can have a huge impact on the decision. So that's why L infinity can be a very tricky, like, or very interesting thing to study. Other norms are also considered, but for the feature space input space equivalence, is just like they are just you don't basically choose. I hope it
Okay,
clarifies.
thank you. Another question from Jero. Are these robust methods and your detection approach affected by the distribution from which the noises are sampled? Because you
Mm.
said in the beginning, carefully crafted noise.
So can you come again with the question?
Are these robust methods and your detection approach
Mhm.
affected by the distribution from which the noises are sampled?
Okay, I don't know if I understand that well, but you can ask a follow-up question if I don't answer it. So the when you have a robust model, you have it. It is robust. You can evaluate it with respect to any type of noise normally. So the noise we consider, noise in general, we don't care about the distribution of the noise. What is important here is the magnitude of the noise. That's why we define it in terms of L infinity norm or LP norm. That's why we define. So no matter the noise distribution within uh, that LP bound, it should be the robustness should be everything that I said or about robustness and everything should holds. But one thing to note that the type of norm determines the type of robustness. So if you are robust to norm 2, you will not necessarily be robust to norm L infinity, or you are robust to L infinity, you are not necessarily robust to L2. But if you are within a certain threshold, no matter if it's random noise or if uh, uh, it's carefully or whatever what's done. I said carefully crafted. It has to be carefully crafted because in general, it takes a path that the model it takes a path that a corner that the model didn't see. For instance, because the loss landscape is complex, or the decision boundary is complex. So if you want to attack it, you are kind of adding noise in a specific way, as I was explaining when we are attacking. You attack it so that it goes in a certain direction. If you just apply noise in with a certain distribution, uniform distribution, or something, it might not. The model might, depending on how it was trained, it might be robust to it. But then this is the type of robustness there is different. So there are other types of robustness. There are robustness simply to random noise. You have robustness to some common corruptions, which are like when you blur an image, or when you add some if you add some Gaussian noise to it, or you add some fog or any climate perturbation. These are also different type of perturbations. But in general, these one, or even like image manipulation techniques, like increasing the contrast and everything, these are specific types of perturbations that, if they are within the threshold that you have set, that means if your threshold if the magnitude is not high, you fall into what I'm talking about. But if it's bigger, then you don't fall into this case. But it's still called, sometimes it's still called adversarial examples, because if you just like the graffiti examples I told at the beginning, you can add a graffiti on a stop sign. Probably the L infinity norm will be bigger. Sorry, interruption. Sorry for the interruption. So if you add, so the magnitude will be bigger. So it's still considered adversarial, because there's no significant change in the image, but it still stays, but it still misleads it. So the robustness is very specific. That's why I started by defining specifically what I mean robust. It is only noise, or any kind of noise, no matter the distribution, that stays within a certain epsilon bow. I hope I answered the question. I'm sorry for the interruption.
It's okay. So we have another question by Lionel. Can you read the questions yourself or not?
Oh, okay. Let me see. I wasn't sure. Okay, GFC is in the feature space. It's related to Lipschitz constant. Can you comment on this? How is it related to margin consistency? So for everyone's, so the GF here is a distance. So it's a norm in the feature space. So for everyone's interest, I will just show what the Lipschitz property is, and then the comment I made about it, and then tell you. So for those, so the Lipschitz property says the following: if for any function, that's how it is defined. So here you have, so this difference here is the input change, and this here can be seen as the DFZ that you saw, but here it's not exactly the if you put H here, then you have the Lipschitz property for the feature extractor. So the Lipschitz property says that you cannot change, the output cannot change, will change by a maximum value of this factor here. So for robustness, what does it mean? Is that it means x prime, if you add some noise to x, you get some x prime. So attacking a sample or noise perturbations is kind of adding some obtaining some x prime. So this variation cannot bounce the change in the output. So if you have a big, so if you have a big constant here, that means the change in the output will be bounded by the by a big change. But the interesting thing is that if your L is small, so for models, when L is small, you know that this output change cannot be big. So there are models, specific models that are trained. So as I showed, like these models here are trained, different techniques are trained to obtain a small margin, a small Lipschitz constant. But there are also like methods to obtain directly one Lipschitz model. So for these specific type of models, you certify that your change, you will not have an adversarial example on a specific sample, for instance. You can set, so the model is trained in a way that you can prove that the Lipschitz constant is 1. So in this case, you would not have, you will never have an adversarial attack on these samples. But it's have some limitations. I will not go into that now. Then, so this is the Lipschitz. Now come back, like what is the relationship with the margin consistency? Is that robustness means I cannot change that much. But margin consistency means I will keep the order. For instance, if I have my two samples, one is closer to the decision boundary than the other one. If you want them to be robust, when you project them in the feature space, you can put them at the same distance or even like in reverse order. If they are far from the decision boundary, that's sufficient for the robustness. That means you just put them so that you cannot change it that much. But in certain models, this order can be preserved. That means the projection will, so the feature extractor will put them exactly where, I mean, not exactly, but proportional to where they were in the input space. So that's the margin consistency. So the only thing I can say about the relationship here is that Lipschitz smoothness does not imply margin consistency. And also, it is not because you preserve the order that you also robust. So we've seen, so the results that I haven't shown here is that if you have like small, you have standardly trained model that are not robust, uh, that can be margin consistent. That means they kept the order, they preserved the order, but basically they didn't, they are not robust because all the samples are close to the decision boundary. So I cannot say more than this about the relationship. It's probably studying this more can give more insight into what is happening there. But yeah, that's basically the relationship between these two.
Okay, I hope that is clear for everyone. I have a question. So, if I recall correctly, in the beginning you said to calculate the or to estimate the margin, you look at the output, so the logit output and the next to output for the same instance. Is
Okay,
it?
yeah, yeah. To estimate the input distance, right?
Yeah,
Yeah, I will show you on the picture itself. So you see, the estimation is the red one here. You can see the black one is the true distance. So if you
yeah.
can see already, the black in black you have the true distance that is intractable for deep neural networks because of the nature of the decision boundary. But if you attack this sample here, you get
Mhm.
an adversarial, which by definition is close to the decision boundary. Basically, what we are doing is considering that this distance in red here is an approximation of our black part. So if your x1 is very close, if your x1 prime here was very far here, you would see it's not a good approximation. You would know that. So the better x prime you get that is close to the decision boundary, and then the better you have, the better your approximation will be. So
I
that's
think I was talking about the logit margin instead.
the logit margin. Okay, great. The
Yeah,
difference. Okay, so the logit margin, it's the difference between the biggest logit and the
yeah,
second biggest logit. Yeah, yeah. So
yeah.
that's here. Yeah. So
So, meaning if I have an instance
mhm.
and then I am predicting it as a, I don't know, amongst which I have 10 classes. So the
Yeah,
logic margin would be the difference between the first prediction and the second. So the first and the first two logics, right?
the two biggest. Yeah, the first
Yeah,
two that if you rank
logics.
them.
Order, yeah, if you
Yeah,
order.
yeah,
So I was wondering how your your technique can then be applied in a regression setting where you are predicting a single value.
yeah. Yeah. So that would that so the logit margin here is specifically defined
Classification
for
problems.
classification.
Yeah.
So and everything here is valid for classification models only. And so uh, you could attack also like any regression model for sure, but um, it is yeah I'm not sure how the margin consistency would be defined there, but yeah, in this case it's more we are more exploiting like the structure of the problem basically,
Yeah, yeah.
because you have decision boundaries and you have classes and yeah, so
It's
it's
okay.
not yeah, yeah, sure.
Okay, so we have one last question from Bertrand,
Mhm.
which is a more relaxed question in his opinion. So he said he saw in here on your first slide. Are you sometimes in France?
Yeah, so thank you for the question, and I think I'll take the occasion to thank uh, my team also. So the project, and maybe tell a bit about the project I'm working on. So so this work is
Collaboration.
yeah, it's in a larger project called Deal here. So the Deal project is it's which is for dependable and explainable AI learning. And so it's a project that is in collaboration between France and Quebec, that was initiated between France and Quebec. So the objective is to uh, build or study models, AI models for safety critical systems, and especially in domain of transportation, aeronautics, for instance. So I have two supervisors. So one supervisor is in France at Université Côte d'Azur, and the other one is at Université Laval and Mila here. And so I haven't had a chance to go to visit his lab yet, but every year we do have um, uh, a conference called Mobility AI, which is like AI uh, in transport systems and aeronautics, basically. Every year is like it's either in France or in Quebec. So this year it was in Montreal, and last year it was in Toulouse, and I was there in Toulouse, but I haven't had a chance to visit my other supervisor's lab yet. Yeah.
Okay. So are you sometimes in France? Yes. Because maybe Bertrand
No,
wants to
not
know.
yet. Not yet. When I'm in France, I'll let you know. But
He said you were in Toulouse last year. He's
yeah, I was
asking.
in Toulouse. Yeah, yeah. I'm sometimes.
Perfect.
Yeah.
So you have a great job from Mikael. He says, "Great job, brother." So I think if there are no other questions, we might maybe wrap up here.
Oh, I saw a question that from Pauline quickly.
Okay.
It says, "Is
Oh yeah.
outliers could have impact on your results?" Yes, yes, that's something we haven't evaluated. Of course, what we are measuring is on clean samples. If you have a clean sample, you can. So it's like clean samples, IID. If the data is no longer come from IID with respect to the training data. So if your data is no longer IID with respect to the training data, if you have we're talking about outliers. Uh, so first, let me finish about that. So if your distribution changes, so if it's not longer IID, then you cannot. I don't think you apply it, or at least we haven't evaluated it. But now, in terms of how we estimated the metric, like the Kendall tau, we specifically shows the Kendall tau because it's a correlation rank that metric that is more robust to outliers than, for instance, the Spearman rank correlation. So it's more robust to outliers, and we made sure that the results is more robust. For instance, by taking when we estimate the distances, for instance, we only in practice we only look at the samples between the fifth and the 95th percentile. So that's yeah to make sure we don't have outliers there. But the Kendall tau itself is quite robust to outliers. Thanks.
Okay, thank you. Sorry, I missed this question. So maybe one last question.
Mhm.
So since your method is mainly for inference, I guess it's very fast then to test how robust the samples are.
Yeah. So the main I would say benefit of using so first of all, it's a property that you can test for your model. It is not as cheap as you may think to measure if the robust to measure if the model is margin consistent. You could do it with few samples, but once you know that your model is margin consistent, you just need a forward pass to you just need the forward pass. It's like the forward pass is the same time you need to make prediction. Once you
Yeah.
make the prediction, you instantly know if your model can be attacked or not. Also, yeah.
Okay. Okay.
Thanks.
So great work. Great work. Thank you very much
Thanks.
for presenting it with us here. I guess there are
Thank
no other
you.
questions. So maybe what could be a real life example adversarial attack?
Oh, uh, I presented it at the beginning. So adversarial attacks are more like a weakness of models of today's models. So as I said, it's in all you can see the literature and I can give pointers to it. So it happens with in a lot of in all the domains of machine learning. Wherever you use whatever model you are using, it can be subject to adversarial examples. Whether you are using models like voice or anything, and people are studying that. And for instance, even with large language models, whatever they produce can be also subject to adversarial attacks. Probably the challenge that, and in my case for the vision classification task, is the is their impact on self-driving cars, for instance. If you have a self-driving car, the model is somehow making predictions on if this is on the stop signs, on whether this is a person or a pedestrian, an object. So it's perceiving. So if your model is not robust to this kind of small perturbations, then it's a major risk. So we have cases of uh, self-driving cars that I won't cite, famous self-driving cars that I won't cite here, that were tested and then they crashed. We don't know why they crashed, like, or they suddenly become it was on test, of course, but it could be adversarial examples. So it's kind of a weakness of the model that in your general usage of the models doesn't matter that much, but in safety critical systems or sensitive systems, it could be very, very critical. Yeah.
Okay. So for some reason, people don't want you to leave.
Oh, I don't mind.
You don't mind staying here to
Yeah,
lecture us.
so, if people are interested.
Um,
Uh,
there are no further questions.
yeah.
I don't see anyone coming.
Okay.
So yeah, maybe finally, we can wrap it here.
Okay.
Okay. So okay, as I understand, your method is yeah, it's used or employed at inference, and it kinds of gives confidence intervals or like kinds of give confidence about the predictions.
Yeah.
So I think in the end, it's a very useful topic that you're having here, and we hope that you can pursue it such that when we use packages to train and predict models, then we can report the prediction accuracy and say, oh, by the way, my model is margin consistent, so you can trust whatever thing comes out of here. um okay, so we have another question coming in. Seems like no one wants to go home. To measure the robustness on subsample, do you at least use one example from each class?
The robustness on the subsample. Yeah, yeah, because yeah, so I think it's about the robust estimation from subsample. Yeah, because I randomly uniformly ran. So I sample at
500. Yeah.
so it's basically you'll have so the total you have 10 classes, so you roughly have oh sorry you roughly have 10 examples per class if it's really uniformly random. So it's uniformly at random. So if you are in an example where you have if you are in an image net where you have 10,000 classes, 1,000 classes, the validation set there, the test set there is like 50,000 also. So if you had to take one per, if you had to measure one per class, you at least need 1,000 samples. Otherwise, yeah, it would not be, yeah. Otherwise, it will not be representative. And I have tried this case where you just take, you measure just on one class, and then you will see that it's not really margin. Like the measurement will not be accurate, and it will tell you that it's not margin consistent when it is. Or yeah, that's the that's the.
Okay.
Yeah.
So there is a kind of effect on the heterogeneity of the sample then, or
Yeah,
an effect from the classes themselves.
yeah, it seems it's more like your samples are so because samples of the same class might tend to be represented in the same area, right?
Yeah, true.
So it seems like your estimations in if you estimate only one class, you may not see you will only have maybe similar distances that may not tell you exactly how the margin consistency is, or how your it's like if you were evaluating robustness or anything else, then you cannot yeah then you cannot accurately evaluate it. But he's saying, did I try it on unbalanced data set? So unbalanced data set, no. I haven't tried it. And actually, if the data is okay, if the test sample that you use to measure it is on imbalance, then I think you might not accurately measure the I mean, I would suspect it will not accurately reflect
Margin consistency because
yeah,
it comes back
but
to
for
the
robustness, it doesn't matter. When you want to know if the sample is robust, it doesn't matter. You just attack, or it doesn't matter it's robust or not. Doesn't depend on which class it is. So the evaluation, but if you evaluate on just some samples, you cannot say, even for robustness, you cannot say this model is robust at 80%. It's like for accuracy, like if you are measuring the same thing as when you measure accuracy, if it's in balance, then you cannot, because the model may be perfect. If you predict all the time the biggest class, like the class with the largest number of,
majority. Yeah.
then majority class, then you will assume, oh, this model is 90% accurate, but then it is not somehow. So it's the same kind of bias that you have. You just And the assumption here is that you will have a more a balanced data set somehow to measure your thing. So yeah, but I haven't tried this unbalanced data set, and I think it wouldn't be a
Too
good
hard to try.
approximation. It wouldn't be hard, but it wouldn't be a good approximation of the robustness or the margin consistency.
Okay. Okay.
Yeah.
Um. So, are we done asking for the people in the comment section, or are we still here? Okay. I think now we can wrap it up. Do you have a word to end the presentation,
Yeah,
Jonas?
yeah. So I just wanted to say, as I said here, if people are interested in knowing more, like the question about how do you make this noise, that's a whole another set of
Yeah,
techniques
another
and
field
everything.
of
If you
study.
want
Yeah.
to know more about like how the adversarial examples work or anything, could be another time if give to the people what they want. That would be my last.
He gives to the people what they want. So please reach out to him if you need anything.
Yeah, yeah, you can reach me. Feel free to reach me. I'll be happy
Okay,
to give you more pointers.
perfect. So let's call it a day and thank you very much again, Jonas,
Thank you.
for first your work and your efforts, and then secondly for presenting it here. And so we wish everyone a nice end of Saturday and see you next week because we have another presentation next week. Yeah, from another very good researcher. And so we'll be very happy to have you guys again next week for the next presentation. So have a nice end of Saturday and nice weekend as well. And see you next week. Goodbye, everyone.
Thanks, Liz. Thanks. See
Thanks,
you.
Jen.
Bye.